so that's recording, downsizing, going to the lesson on banked corners. Oh, that's good. Okay, I might have to close some stuff, or at least restart that one. Apparently, banked corner with friction. Let's give my computer a break here and close some of these lessons I've been planning. All right, leave that one open maybe because we need it. And we're going with bank corner with friction. All right, you can see the screen I'm sharing? Everybody, yes, someone respond?
Yeah, I can see it.
The window and the smart notebook loading and so on, okay.
Yep.
All right, banked corner with friction. So we saw the bank corner stuff, and we know there's like an ideal speed, like this, a certain speed, really, an exact speed that is necessary for you to like stay at the same height, traveling in a uniform horizontal circular motion, right? If you go too fast, then you go out to a larger diameter circle, which means you're higher up on the bank. And if you go too slow, you collapse down into a lower, a small lower circle, and so you're lower down in the bank, right? So with that specific speed, you can stay in stable uniform circular motion. So if we have friction, then what happens is you could think of the friction as being either to hold you from going out further, right? If you're going faster than the ideal speed, or if you're going slower than the ideal speed, the friction would be holding you from falling down, right? So there's going to be two cases as a result. There's going to be the going too slow case, in which case going too slow for the normal force in the ramp to be the perfect amount for uniform circular motion, in which case the friction is holding you from falling down, so the friction is pointing up the ramp. The case two is, of course, if you're going too fast, right? For uniform circular motion, to have the right speed for the circular motion, in which case the friction is going to be holding you from spiraling out, so the friction is going to point down the ramp. Okay, so then that makes our free body diagrams be a little different. You're going to have a different, first of all, let's just look at this part. Let's kind of like, don't worry about any of this for now. So we have fairly normal stuff in our thought process here. We've got this banked corner, so that's the angle of the ramp that we're driving around and around on. Like a circular track, or it could just be a portion of a circular track, like a corner of a banked highway, on or off ramp or whatever. So the new part is we have friction, right? So we have friction is up the ramp in the too slow case, stopping it from sliding down, right? And so we still have a gravity force, though. We still have a normal force. We still have a component of the normal force towards the center of the circle. We still have a component of the normal force that's up, right? Now, the way this diagram is drawn isn't actually quite right, because issue in this case, and so I'm going to show you here now that the normal force y component won't actually be equal to gravity anymore. It used to be. That was our driving idea in the original case. So this is actually just a copy of the diagram from the no friction case, right? So our driving principle to get started in these questions was that, hey, we're not going up or down off of this ramp, so that means that this force and this force are going to be the same, or else we'd be accelerating up or down, right? Can you see why this is true now? That the normal force in the y component's not just going to be equal to gravity anymore? Is anybody key their mic, tell me why or no? Look at what forces there are in the vertical direction. There's only three forces here, right? And actually before there was only two. There was the normal force and there was the gravity force. And so this component vertically must have had to match the gravity force, because basically forces have to balance out. If you have no acceleration, The issue now that I was hoping someone would notice is that since we have a friction force that's on an angle, then there's actually a component. Let me ungroup maybe that so I can fit things in here. I'm going to do a little fancy maneuvering here. Group that. I need to just sort of shrink that guy down, or I'll put it at the tip of it actually. So that's the friction force. That's supposed to say FF. It's a little bit hard to tell. But the issue is that FF has a component that is, let me try and draw here. It has a component that is sideways, and it has a component that is up and down, right? So the issue that we have is now there's going to be, this thing will let me draw properly here, up in there. I'll move it in a second, but that's y component. Okay, so that is why things are a little different in our analysis now with this friction case. We have a y component. So basically now we know that the net force in the y direction is still 0 because we're still in horizontal uniform circular motion. We're not accelerating up or down off of the ramp or anything, but it's because there's a friction helping hold us in place. And so now we've got the normal force in the y direction. That's this green arrow here. We've got the y component, vertical component of the friction force. That's in here. And then we've got the gravity, right? And so basically, you can see that friction's sort of as part of this. So I guess what you'd have is you'd have the normal force and its component be a little smaller because this is helping, right? So I guess if we were to try and correct this diagram, we could shrink this down. We could shrink this down. Let's shrink that down. And then if we stick the friction force on the end of that one, so let's draw a little FF y component there, and then we can say, okay, so now we've got, I'd be in danger of making a mess of this diagram here, but let's put a vertical stamp there, and there, you know? And so then basically this is what I want to draw. I want to draw that and that are the same. Okay, so notice that the normal force component up and the friction force component up are balancing that gravity force. So that we have a net force of 0, and therefore we have that acceleration of 0, which is necessary for, so this right here, let's go F, you know, in the y direction, you know, equals the F in the y direction. I don't know how to draw that otherwise. Does that make sense though? These are the same as each other. And that's necessary, like I said, for this. If it's uniform circular motion, that means there is no acceleration in the y direction. Talking about horizontal uniform circular motion, so there's no y acceleration, and so these forces have to balance the way we're showing. Okay, and in contrast to what we did before, right? Before, let me just group those two. Before we had a bigger normal force. We had a bigger normal force because then the component balanced gravity on its own just from the normal force, right? So anyways, let's move that back to the west. Any questions about that right now? So for each situation we're talking about here, there's actually going to be a minimum and maximum speed possible. Because the friction can help either way, right? So this is going to give us, this one would give us what, the minimum speed that we can do once we solve for things. And then this one's going to give us a maximum speed. And so in this one, the difference is, like we talked about, the friction is going to be pointing down the ramp. So it's helping hold it from going out too fast. If we're going too fast for perfect uniform circular motion speed, then you've got some friction holding you in place. And in these cases, you're going to feel yourself in the car, like having to hold yourself from falling down the ramp, or having to hold yourself from, you know, getting thrown to the outside of the car in the corner. You start to feel that, oh, you know, and you're holding on for dear life as you go around the corner, right? So now, because the friction component's down, then we still have the same logic here. It's just that, let's add something in here. This number right here, numerically, is going to be down the ramp in this, or down actually I should say, so this is going to be a negative number because it's just a y component, it's not down the ramp, it's just down. And then this is going to be a positive number because it's up. Right, so we're used to that. We're talking about all the forces added up, and then you put them in as the appropriate signs, and everything makes sense. Okay, so again, same idea here. Friction, we already mentioned this, right? That the friction in this case, of course, is down the ramp. So because you're going too fast, it's stopping you from sliding up and out. So I have to do the same trick here. I have to shrink this down so that it looks like it's supposed to for this case, right? Actually, I'm shrinking it down, but I am actually doing the opposite of what I should do. I said shrink it down, but I actually need to make it bigger, because in this case, you can see that this force here, this y component down of the friction, it's red this time. Move that down there. It looks like I undid two things at once there, but anyways, that component downward there, y component, you can see the way this question is drawn here, that again, we have that same logic, right? That this vertical amount up is going to balance that vertical amount down. And these guys here, that's the same as each other in order to have no acceleration vertically. Okay, so that's the weirdest part of this, is that you have to consider the friction's component up, and the frictions also, in a second, we're going to be looking at the friction's component sideways as well, because it's going to contribute to the amount of force available for circular motion. All right. So let's do this. Let's do an example here. We're looking at the slowest speed possible now. So this is the same ramp as before. We have an 80-meter ramp. We've got a 1,000-kilogram vehicle, which we don't actually need, but we're going to have it just to make it the calculations seem more real, rather than everything being like M with a 9.8 and so on, right? But just get used to, like we should be aware that we don't really need this. I should be specific here, not needed for speed, right? It is for forces though. Okay, so, yeah, if that makes sense to you. You don't need it for speeds, but you do for force values. Anyway, so let's go through this. Would it slide? Oh, this is my first analysis here, was just basically, would it slide down the ramp if it actually just stopped, right? And just to analyze out like the slowest speed possible, I suppose, could be any speed. It could be like 0.001 meters per second, and it would just be able to drive in super slow uniform circular motion, right? I think this is calibrated so that basically if you stopped, you'd slide down there. It's a fairly slippery ramp. You'd actually slide down the ramp if you stopped, right? And otherwise, your minimum speed would be 0, essentially. You just stop, but then that's not technically uniform circular motion either, is it? So I have an analysis here where we're looking at what we have for forces. So let's put here first. Oh yeah, I want to make sure you recognize that this free body diagram isn't for uniform circular motion, right? Or else we'd be setting the y components equal to each other and so on, right? This is for basically if this is a ramp and we're like seeing what would happen if we stopped and let it slide, right? And so we're going to be checking to see if the gravity component down the ramp is bigger or smaller than that friction force that's available, okay? We're hoping that the gravity force, to make this question make sense, right? We're hoping that the gravity force is bigger than the friction force, so that it'll slide down, in which case there's a certain minimum uniform circular motion speed that's possible. Usual deal, choose your X and Y direction based on the ramp in this case, because that's the way we'd be accelerating. I think you'll see in the free body diagram here, we kind of have two direction systems. right? We've got like the x direction for the acceleration of the uniform circular motion, but then we had like the direction of the ramp, and that's the weird part about these questions. So we'll keep analyzing here. I want to say, of course, friction is equal to mu Fn, right? Fn we can analyze will be equal to, you can see in the diagram here, the normal force will be equal to the y component of the gravity because we're not accelerating up or down off the ramp. When we're sliding up or down it, we're not going up or down off of it, right? So acceleration in the y direction is 0. The usual business here where we're saying, okay, so that means the net force in the y direction is 0. And so my normal force is equal to my opposite of my gravity force. Okay, so that's going to give us the ability to calculate the gravity force and therefore the friction force. So our usual stuff, looking through things here, you know, that's the 30 degrees there, you know, through an angle analysis, you can end up saying, okay, that's the 30 degrees where that black dot is. And so we're talking about being adjacent to the cos, adjacent to the angle. So we're talking about cos. So it's a 20-degree angle, a little small there to be able to see, but I went up to remind myself. So the gravity force times the cosine of the angle gives you the component of it, right? The vertical component. So that's your normal force. And so usual stuff. Mu Fn gives us the friction force. Right? So we have 920.9 newtons of friction available, and we just need to check and see what the component of the gravity actually is. So I guess that would be the sine of the gravity, right? In order to get the horizontal component or the component down the ramp. That should be there. So basically we're saying if the gravity is greater, then it'll slide down without a certain amount. And so we look at the gravity force, and the gravity force down the ramp component is 3,351.8 newtons. So you can tell it's not going to be able to just sit there on this fairly slippery ramp, right? It's going to need to have some uniform circular motion in order to actually stay at the same height on the ramp. Okay, so this is just an analysis. If I just gave you this question, right? I said, what's the minimum speed possible? Then basically you can trust that I've made sure the numbers make sense. So you can go ahead and make the assumption that uniform circular motion is necessary and so on. I just wanted to show you the details as like a peek behind the curtain, if you will, right? But behind the scenes, I had to make sure that I had numbers that made sense to ask you the question. So, and it gives us another opportunity to compare the two different kinds of free body diagrams, right? In this one, okay, watching carefully here, in this one, this force balances this force. Oops, this force, right? Because we know we're not accelerating vertically off, right? In the next free body diagram we're going to do, we're going to go back to the vertical forces being balanced, meaning like true actual up and down vertical forces being balanced because we're in horizontal, you know, circular motion, right? This direction, okay, so along with this normal force, there actually is an acceleration in that direction because of circular motion. So we can't balance, we can't say these ones are balanced if we're in circular motion. Because if you look, there's certainly an acceleration towards the center, which means there's a component, I'll draw it on here and then erase it after so it doesn't mess up this diagram permanently, but picture the component of that, you know, there must be a centripetal acceleration, right? And so there's actually a component of that centripetal acceleration in the direction perpendicular to the ramp. So you have acceleration towards the center, but you're not going towards the center, right? Because you're in circular motion, you actually travel around and around. You don't get closer to the center, I should say, even though you have an acceleration towards the center. I think we're getting to be okay with that, hopefully. By the same logic, you can say here, like I'm accelerating up off the ramp, technically, but I'm not actually lifting up off the ramp because of my actual motion being circular. Please ask questions if I haven't, if you need, if I haven't done a good enough job setting this up. All right, hopefully that's good news. So what's the minimum speed for uniform circular motion? So we're going back to a free body diagram where we are, now this isn't necessarily drawn to scale, right? But we are going to set it up. We're going to mathematically end up setting it up so that this stuff, let's put it this way, this stuff balances this stuff, right? So we're going to end up having it be where the up equals, you know, the down. So the total up and the total down balances, right? Okay, so the total number here and the total number there are balancing. That's going to be our driving principle in this case because of this, right? For a uniform circular motion, the true vertical stuff actually balances. All right, so that's this statement here. We have the normal force in the y component, friction in the y component, gravity are all balanced. Okay, so what do we have here? Yeah, because we're in uniform circular motion, like I said, we have that vertical acceleration's 0 this time. So they're going to be balancing. So we're going to have what? We're going to have that y component. This isn't any different than what than this line. It's just that I have the 0 in there. Okay. So we do have some numbers, thankfully, because we have that mass. But this could have been listed. I should do this all the way along. This could have been just listed as M 9.8, right? So M 9.8 is our negative 9,800 newtons. That it just feels so much less stressful to have a number rather than a mystery M sitting there. I just revealed there to you that, of course, we know there's in the x direction towards the center of the circle, there's an acceleration. So, any questions about that part? Does anybody want me to leave that page a little bit more, or are we good to move on?
I need it a little bit more, please.
Yeah, absolutely.
Yeah, thank you. Thanks.
I certainly wait. I could add on to here those fancy brackets. Basically, we've got those two things, right? And we've got the positive number and the negative number that again are the same as each other, right? So they're adding to 0. That's how it ends up looking in the actual net force diagram. Let me know when you're ready, okay?
I'm ready. I don't know about other people.
Okay.
I'm good too.
All right. All right. Be brave. Key your mic and say, hang on if you need it. Okay, so we've got our concept here that the acceleration in the y direction is 0, and so the net force in the y direction is 0. So all the forces added up in the y direction add to 0, and so there they are, right? Like we had on the previous page, the gravity, the y component of the friction, and the y component of the normal force. So we've got these values. We know that it's equal to 0. We're going to be, say, adding that negative 9,800 to both sides, of course. And we need to have something in there for each of these values. Now, I think we need a copy of this free body diagram over there. So let me see what I managed to get here. I'm going to go over here, paste that in, I think. Group it so that it's contained, move it over, and I can just get rid of clean it up a little bit here. Let me just move this down. So let's get rid of some of this drawing on here. Up, and let's maybe even just have that number listed. There we go. So we've got the gravity force listed, and yeah, so there's our free body diagram that we can refer to as we're saying, oh yeah, okay, so what do we do to get these components and so on, right? So I've got both things visible there now, that's good. So if we're looking at the y component of the friction force, we know that the friction force is mu Fn. I haven't identified the friction as a value yet, because I don't know the normal force. The normal force kind of depends on what speed we're going and all that stuff, right? So we've got the Fn, mu Fn in there. So that's the y component of the friction force, mu Fn. And so I have it as sine of the 20 because we're on the opposite side of the 20 degrees. So it's sine. The normal force here, right? We can go through the angle journey and identify that that's the 20 degrees, right? That's a bit of a process, of course. You have to each time be careful to make sure what angles you're talking about, right? Here, let's just help you with that. We would have an F pattern to be able to see that that's 20 degrees, okay? So that's easy peasy. This one, I feel like there's a little bit more of a journey where it's like, okay, this is 20 degrees because of the Z pattern. And then you could identify this 90 here and say, okay, so that's 70. But then you can say, oh, wait, but this is also 90. So 70 and 20, right? 70 and 20 has 70, and that has to be 20 in order to add to 90. So if you're needed a little bit of a recap on the angle craziness, that's the two ways that you can identify those things. So anyways, sine of the component, right? Sine as part of the component to get the opposite one there, and then adjacent to get the vertical component of the normal force, which is the 20. So that's why that's Fn goes 20. So hopefully that helps you a lot. We end up with then a screen that I need to get control of here. Let me just try my best to get control of this thing. It's funny, actually, I'm trying to get control of my screen, and then yet I've got this thing on there about the Teams meeting saying give control. That's not the same thing. Just control issues. Anyways, so the 9800's there, and we've got an Fn in both these terms. So mathematically, if I common factor that out, then I can solve for it, right? So basically, those just become numbers. I get determined values at that point, 0.1 times sine 20 plus cos 20, get that as a number, divide it out on both sides. Gives me a normal force of 10062.7, 10,062.7 newtons. Okay. So that is the normal force. And notice that what we did is we basically have calibrated this to be like, okay, we've got zero acceleration vertically, and so this is what that normal force has to be in order for that to be the case. So we're getting the numbers. This was just that friction stuff. Escape really there, I think, because the way we analyzed it, at least anyways, should be fine. Because I showed you the angles and I justified for opposite or adjacent and so on. And then the friction force ends up being 1006.27. Okay. Friction is 1006.27 based on that normal force we calculated. So our next step, I'll come back to this page in a second, but our next step is to say, okay, so what kind of circular motion are we going to have? We're going to equate our net force in the x direction to be our centripetal force, and that'll help us figure out the speed. Okay, so let me know when you don't need this page anymore. Okay, I know a couple of you probably are brave enough to key the mic and say you do need it. Let me know when you don't need it.
I'm good for now, thanks.
Okay. All right. Let me know if you need it. Anybody else? All right. So now we've got, we can figure out a net force in the x direction. So that's going to be this. What's that going to look like? It's going to look like whatever forces there are in the x direction, add it up. So if we go back here and look, be like, oh, well, there's going to be an x component, and there's going to be of the friction force, and there's going to be an x component of the normal force. Now, our x direction we're talking about now, of course, is for the uniform circular motion towards the center of the circle direction, right? Whereas previously we were talking about components. Actually, it still worked out, right? Sometimes we talk about the component relative to this ramp angle. That's all. Anyways, so there's our x components. Right, friction x component, normal force x component. So we can figure those out. We've got a number for the friction force, and so we can figure out the component of it. We do the cos 20 of that friction force, because, or is it cos 70? And it looks like cos 20. So I should do my numbers a little nicer there. So that's the value we get for the centripetal force, right? And so the next step is going to be to say, okay, well, those components add up to a value. That's the value I have for my centripetal force. Luckily, we developed recently a formula for that, mv squared over r. Okay. So at this stage here, this is where you can kind of see that the masses would cancel out, because I didn't keep doing it all the way through, but I did say here, I said, oh, that's really mg. And so wherever there was a 9800, that was really an mg, right? So this was really an m9.8, which means that this was really an m9.8 divided by whatever the heck this number became, right? And so you can see that this has an m in it. I'll just do that for now, okay, with the other numbers. So or in other words, it's m with a number instead of what it worked out to be. And every single one of them has that. Okay, so the normal force itself has the m, and the friction force has the m in it because it has the normal force in it. So you can see that we'd have m's everywhere. So we didn't actually need to know the mass of the car. It just makes it seem less stressful having it, because we can calculate the friction force, we can calculate the normal force, we can, rather than it all just being in terms of how much mass there is. But we don't actually need it. So this, this 1000 is needed in terms of this number here. But notice, of course, this number would have been a 1000 times a 2.4961, I guess, right? So if that was, stop moving around on me, goodness sakes. Right, so if this was an m, this was an m, it would just cancel out. You see what I'm saying there? Like basically you need the 1000, of course, if you have the 2000 number, but if your decimal was over here because you didn't have the 1000 in there, then of course you would not use 1000. But anyways, that's pretty easy to solve for R, or sort of for B, right? You got the R value goes in, the numbers go in, and you just calculate it out. Right? Multiply both sides by 80, divide both sides by 1000, take the square root. We end up with 14.1 meters per second. I'll start to show some of this other stuff here. What was this? Some of this stuff was what I've already talked about how the masses cancel out, right? So basically, was mass really needed? Well, no, because I showed you, you don't need it. That sure makes it easier, for sure. Or seem easier, at least. It's actually the exact same work. Less calculations, I suppose, right? If the mass was some ugly number you had to type in, like instead of being 1000, it was 1238.36. Instead of having to type that number in a bunch of times, you wouldn't have to. So technically, calculation-wise, it's easier without the mass. But concept-wise, it's harder. I don't know why I have that doesn't probably really need to be there, but the context of what we're doing here. But anyways, so that is the minimum speed. So if we go back to what the value was previously, it was a bigger value than that. So now we've got like, oh, we could go slower because friction's going to help hold us up, right? Friction's going to help hold us up. So we can go slower. I forget what the number was before. Does anybody have in their notes when we did this uniform circular motion ideal speed? Anybody have in their notes what that was? I can load it up as well. It just may take me a little bit longer. Bank corner without friction, no friction. Bank corner. Actually, the PDF loads pretty quick. So we had bank corners. We had the example with 1000 kilograms, 80 meters, and so on. Blah blah blah. We ended up getting that it was 16.89 meters per second. Okay, that's what we had before. So if I zoom in to that, I might just take a screen capture of that and say, it was this other number, bank corner. corner friction. Oh, it's this one. That's why. So I have to go here, get my screen capture tool. Here we go. All right. So we can just point out that without friction, it was. So notice IE or whatever is slower, right? And the ideal, no friction, uniform motion or horizontal uniform circular motion. How come? Looks kind of weird. Horizontal. I'll do horizontal. All uniform circular motion speed. I think it's like maybe exclamation point worthy there because it's confirming what we thought it should be, right? So it's slower than the ideal, which was previously found. Right? Found that the ideal speed was a little under 17. So we have here there. So to me, that's a big check mark, right? It's like, yep, it's doing what it should. If we did all those calculations and I found a speed that was bigger, that'd be like, okay, that doesn't match the logic of what we've done. If it was bigger than 16.89, right? But it's smaller, it's showing the friction's helping, so you can go a little slower. But you can't stop. Can't go lower than that. If you go slower than this, you're going to slide down the ramp. Friction's not enough to hold you in place. Questions? All right. Do we need that page a little more or no? No? All right. So a new assignment for you to do and hand in is to figure out the maximum speed that you can go. So I have the answer there. I don't know if I want to, you probably already saw it long enough anyways, but basically, so you know if it's done. I don't know. I didn't do it as an assignment last time. I forgot that I put the number there, but anyways, you can see it from the video anyway, so I may as well leave it there. So you know you've done the calculations right, and you can hand it in with confidence if you get a 19.4 meters per second maximum speed it can go. Okay. That hopefully isn't a stressful assignment for you because really it's this same process, right? With a key difference in this area. That's all I'll say. But yeah, run the numbers basically. Okay. So I have 2 questions for you to do, or 3 maybe, I guess, because of the, how does that work? So find the minimum speed here, plus you're finding a minimum speed in this one. All right, actually, sorry, find the minimum speed there, which is the same as before, and then find the maximum speed for that one, and then we have this one here. If the speed was increased with everything else the same, what coefficient of friction would be needed? The solution. This. I would just warn you that's a bit tough. I'm gonna say, like, I'm gonna remind you, don't be afraid to like look at the solution and use it to help you get through this one. Okay. So there's one more minimum to do for practice, maybe as a first step for you. Then try to do the assignment with the slight difference to make it a maximum speed. And yeah, and then after that you can try to solve for that coefficient of friction. But it's kind of nasty because you end up with variables in multiple spots. But it does work, and I do have the solution worked out for you, and it'll be posted. So that is the banked corner with friction stuff. Good to go on that? Any questions? All right. So looks like maybe I might have to load this one up too. Why is it doing that to me? It's not the first time I've seen it, but I just haven't identified why it does it.
Sorry, Mr. Horn.
Yeah.
What day is assignment 5?
Yeah. So how much time do we need for that one? Like really, it's tonight's homework is what I'm thinking of. Now let's say by the end of tomorrow, right? You're doing homework and then you're going to hand in part of it basically, right? So let's say by the end of tomorrow, so that you have a chance to try it today and have a chance to try it tomorrow, get help tomorrow in the help session. Okie doke. So I will, yeah, let's do that. I can even actually go in here and make that thing Gravitation. Oh, wait now. I have to rename these things. So that was, I'm calling that assignment 5, I guess. Is that right? Keep track of things here. Assignment 5. So I'll have to rename on here assignment 5. That's all. Yeah, I'll do that in a second. But actually, I may as well do it now before I forget. Call this assignment 5. And it's max speed, right? Assignment 5, max speed, horizontal uniform circular motion with friction. Which one's which there? And that's going to be due tomorrow at 11:59 p.m. Please hand it in on time. That box will close. All right. So then I'll rename these things 6 and 7, I guess, when we get to giving those out. And we'll decide on fair dates for those when we get there. All right. Questions other than that? All right. Okay, so universal law of gravitation, and then orbital motion. So basically what it gets us to, I said basics for now, but we've already done that, so I'm not reviewing it a ton, but basically we're gonna review it and use it for orbital motion. So if you think of, the moon, for example, what type of motion does the moon have? Clearly it's got uniform circular motion. It just keeps going round and round, right? So based on what you know about the moon and so on, what do you know about the net force on the moon? So the moon's in uniform circular motion. So maybe the first thing you might say is it must have a centripetal force on it. And then that's that part there. What force provides that net force? And the way we're framing this right now gives you a better idea of what they talk about when they mention like the idea of Newton and the apple falling on his head and so on, right? What Newton realized is this: what provides that centripetal force of, obviously, I'm hoping everybody gets that it's gravity, right? And so when Newton realized that gravity was holding the moon in place, he basically realized that he could learn a lot about gravity because of that, right? How long it takes the moon to go around. There's measurements for how far away the moon is. So we've got the V, we've got the R. It allowed him to determine values to do with gravity. I'm not sure if that's exactly historically when the 6.67 times 10 to the negative 11 for the universal gravitation constant. I'm not sure if that historically that's exactly when that was determined, but you can picture how he'd be able to determine it, right? Because he'd be like, I can measure the speed, I can measure the radius, I can measure, and so I can determine what force is needed, and so I can figure out the universal gravitational constant. Or maybe they use a constant that allowed me to get the mass of the moon, whichever the case may be. Anyways, so just as a quick review of this, we know that the force of gravity between any two masses clearly depends on the size of the masses. If we had bigger masses, you're going to have more gravity. The further apart they are, the less the force is going to be, but it turns out it's proportional to the 1 over the distance between them squared. It turns out to be an inverse square law when you study it. So if we're looking at the masses like M1, M2, and so on, if we look at the trying to graph these and try to get a straight line, it turns out you have to graph the masses times each other versus the 1 over r squared in order to get a straight line, which is how they discovered this equation. Once you get a straight line, oh, there's my constant proportionality. There's my universal gravitational constant. So that constant proportionality turned out, when they measured the slope based on doing a bunch of experiments, to be 6.67 times 10 to the negative 11. And that's where that number comes from doing measurements. These are just hard to do in a physics lab, let's say, because the forces are so small. Even if you had 1,000 kilograms and 1,000 kilograms, a meter of part, just the amount of force is so hard to measure. So I suspect it was done with bigger bodies and so on, bigger masses like the moon. So we've got that the force of gravity is proportional to m over r squared. And of course, we know proportionality constants kick in to give you things are equal, right? It's like in grade 9 where you had like y is proportional to x if you've got a straight line, right? And so then you say, oh, well, that's m, and we know m equals y over x. And so it becomes, it gives you like y equals mx, right? Same logic. I could have done it here too, where it's like m over r squared equals g and or whatever, right? So gmm over r squared, just justified again for you a little bit more. That's your universal law of gravitation. So be able to do calculations with that. It's a piece of cake, except for the numbers are ugly, right? Because you've got the mass of the Earth is like 5.98 times 10 to the 24, and the radius of the Earth is like 6.3 times 10 to the 24, I think it is, and then the radius is like 5.98 times 10 to the 6, or I don't know. These numbers seem familiar when I see them, but you really just need to look them up and use them. The numbers will become familiar after a while just from doing repeated calculations. So anyway, so this is just a thing for us to recognize here and think about what we've looked at before, right? So previously we saw force of gravity equals mass times gravity. So the issue is that that's only for when you're close to the Earth's surface. Okay, if you're more than a couple hundred kilometers up, certainly you have to start to factor in the difference in the gravity strength, right? Whereas this equation does it for any distance. Okay, so there's the radius of the Earth, 6.3 times 10 to the 6, like I was saying on the other page. And there's the mass, the 5.98 times 10 to the 24. Don't be afraid to Google and look up mass of Mars if you need it, or search through your textbook and find it, whatever. Sometimes in the questions, they'll have it listed. Either way, you're getting the numbers and just calculating. So this is a little calculation to confirm this 9.8 number. So we're going to confirm the 9.8 number by saying, okay, wait, we know that Fg equals mg, right? So we want to see if this is actually a 9.8. So I wanted to actually go this one first. We know that Fg equals mg, right? The little subtle thing here is to recognize that in this equation, even though really there's like just two masses always, right? Mass of the Earth would be the one that's like capital M, and then mass of the person is going to be like the little m, right? So typically this is the big M, the capital M. Right, capital M is the one that is basically, when we're looking at orbital motion, going to be providing the orbital motion. So roughly speaking, we could say here it's the big mass, which makes sense because it's the big M, right? And it's usually going to be the one that's attracting the other object, right? It's going to be the one that's like causing the other one to go around it. And so here we're saying like this is little m here is like your mass. Let me point that out as well. This is the little mass. And that's going to be like the one that's attracted to the Earth, for example, right? So for example, Earth for the big one. And then this is the one that's like attracted to Earth, right? You or any other object, of course, that's attracted to Earth. So big M, little m. So in our regular mg calculations, this would be like your mass times 9.8 apparently should equal gmm over r squared, right? The little m's u, so you can actually cancel your mass out. And then you're left with just the mass of the Earth times the universal gravitational constant divided by the radius of the Earth squared. And if you do the numbers there, it works out to be 9.799. And so that's your 9.8 number. So that's where the 9.8 comes from. It's really the universal gravitational constant times the mass of the Earth divided by the radius squared. And at the Earth's surface, the radius squared is just the radius of the Earth squared. So you get your 9.8. Okay. Or you could think of it as like G equals GM over R squared, I suppose, right? But I should point out that this is force per kilogram, right? And so equivalent to what we saw in the electricity unit, force, let's do newtons. Should I do newtons? Force per kilogram, i.e. newtons per kilograms, I guess, right? But anyways, this is gravitational field strength. This is like, this should be written as like curly G, I guess, right? Gravitational field strength. I don't really refer to it quite that same way, but I think it's healthy to recognize the equivalence to that curly E stuff that we've seen before. Anyway, so that's 9.8. That's where it comes from. Do we need that page a little more? Alrighty. So to make this orbital motion is so much easier than you might be thinking. Really, we know that if the gravity force, Fg, gmm over r squared, is providing the force needed for uniform circular motion, like it is in the case of the moon, right? Picture the moon has a big gravity force on it. And we know that this is in circular motion, right? In uniform circular motion. So F net equals Fc. And we know that F net is really just, this is the only force on it, right? So that means that this must be equal to Fg. We're just basically getting Fg equals Fc, right? So we're going to say like gmm over r squared equals mv squared over r. That's the equivalence that we know. And so we're going to be able to like, oh, look at the masses cancel out. It doesn't matter what mass is orbiting and so on. So the mass of the moon doesn't matter. The mass, the moon is the one that's actually in orbital motion, right? So this is little m and this is the Earth, big M. Right? So you can see we're going to be able to get, the speed, for example, depending on what we're looking for. Okay. So we're going to be doing that same thing on this page, anyways. So the idea of the net force equals the centripetal, and so the gravity equals the centripetal is what we're actually doing on this page here. So Fg equals Fc, like I showed you. Get out of here. All right. So and of course we know the centripetal acceleration is v squared over r and so on. So we can, we're probably just gonna use mv squared over r, but anyways. So uniform circular speed, sorry, right? Uniform circular motion, the speed needed for it, we do what we just showed. Fc equals Fg. So we've got a gmm over r squared equals mv squared over r. So just putting these two concepts together. So algebraically, I'm showing on the fly here that the masses cancel out, obviously. If we multiply r on both sides, that gets rid of this one, of course, right? Let me do a different color there. Let's do the green for that. I'd rather the other ones be different color as well, but let's do purple here. And let's change this to like times r, so it cancels out, times r, so it cancels out. There we go. Just so we can have two different cancellation processes going on. And then eventually I've got an r over an r squared, and so I'm going to cancel that r. Oh wait, no. I just realized I can't canceling that r twice, really. That r cancels with the r squared. There we go. So I've multiplied r on both sides. That obviously cancels this r out here. But then r divided by r squared obviously would just become a 1 over r. So that's that cancellation there. And then the m's cancel out, obviously, by dividing both sides by m. So that leaves us with a v squared equals a gm over r, and therefore v equals root of gm over r. And that is a pretty slick result, right? The speed for orbital motion, those are your knowledge concepts, leads to a formula. Oh, that's just from there. I was like, why do I have a 12 there? It wasn't attached to there, I guess. But anyways, yeah, so there's your speed for orbital motion, which is a pretty slick result, right? Root of g m over r. So if you have a different planet, so this is a capital M in here. Try to make that be more obvious as a capital M, right? But this is just the mass that you're orbiting around, the radius of the orbit, and so on. So let's label this. Obviously, g equals, of course, the universal gravitational constant, 6.67 times 10 to the negative 11. Some people put by accident g equals 9.8 into calculations in assignments recently, and there was a small mark deduction for that, but just I understand how that could happen by accident. But just remember, g is the universal gravitational constant, 6.67 times 10 to the negative 11. I'm not going to bother putting units in there because it's nasty. M is the mass that has an object orbiting around it, right? So mass that say that is attracting the orbiting object. Okay, so the mass that's attracting the orbiting object is that m, and then r is the radius of the orbit. I don't know why they use big R here. It's pretty common, so I went with it, but it's annoying. Anyways, this is the radius of the orbit. We're talking about orbital motion, but that's really just uniform circular motion, obviously. So we're using the fancy word orbit, but it's no different than any other circular motion, just that gravity's providing the force. There. Now it's nice and pretty. There. So that's just a picture of the circular motion, right? Fg equals Fc, just like I did on the moon picture. All right, pause there for a bit. I don't know if it's just. Yeah, go ahead.
Big M is the mass that is attracting the orbiting object, what's the little m?
Little m is irrelevant. It goes away. It's not in the equation. So if I said a Volkswagen was orbiting Earth at a certain radius, or I said a pillow was full of feathers was orbiting Earth at a certain radius, or if I said you were orbiting the Earth at a certain radius, you'd all have the same orbital speed for a uniform circular motion. And it has to do with the fact that all objects fall at the same rate. And so all objects would orbit at the same rate as well, regardless of their mass. Okay, so there is no little m. It cancels out right here, right there and there, it canceled out. So it doesn't matter. Okay, so this little m, let's be clear up here. This little m up here does not matter, right? Doesn't matter for speed, right? It doesn't matter for the orbital motion, the speed of the orbital motion at all. Of course, it matters for like how much force of gravity there is and how much force it would take you to stop it from moving or to get it moving or whatever. Like that's when you're talking about force values, it starts to matter, but it doesn't matter for the speed. I was typing my hand in a bad spot for the screen here. I'm wondering if I can make it look awesome. Doesn't matter for the speed. There we go. Look how good my handwriting is. Doesn't matter for, yeah, the word looks weird. Any questions about that? Moving on. This is the one where I was in the middle of saying actually that here that this equation is pretty handy, right? But I find that it's not one that sticks in my mind. Like to me, the concept here of Fg equals Fc is just as important as the equation we developed as a result, if that makes sense. So on this page, I would highly recommend that you put just as many stars or maybe more beside this like Fg equals Fc concept, as you end up putting on the, this new equation that we have, right? So while you're maybe catching up with whatever you're going to do there, let's load up that equation sheet and add, both of those concepts to it. Right, not just the equation. So equation sheet, I should name this thing better so I can find it easier. But we're going to put orbital motion as a heading, and then put the concept and the equation result. Be the best way to do that. So let's go with, where should I put this thing? So there's our regular circular motion stuff. And then we can add to this now orbital motion. So let's just point out, of course, that that's uniform circular motion where gravity is providing the centrifugal force. And let's just copy those things in there. So let's grab that and this and this. So we're going to say, okay, of course we know we're talking about maybe, let's grab all of that. I'm just going to grab that, like all of that. Good enough for me. Hopefully it's good enough for you. So let's grab that and put it on the equation sheet. It's summarizing the concept that's important rather than just focusing on the equation. Okay. So certainly the F G equals FC concept, it's important for you to be able to know that. And yeah, the fact that we end up with a neat little equation that comes out of that is cool, but it's good and handy and all, but if you don't understand that it's derived from FG equals FC, then you've got not a sufficient level of understanding of the course material. All right. Should just do attendance here quick too. I got no Margot, or do I need to go to the list to show participants? Dawson, Margot. All right. Don't leave. Don't do that. All right. So here. So let's do an example of this. So application, determine the speed at which a tennis ball needs to be thrown sideways from a height of 1 meter on the moon in order to achieve orbital motion. All right, so if you ever manage, in your life to go to the moon, that'd be pretty cool. Bring a tennis ball with you, and we'll calculate what speed you'd have to throw it sideways in order for it to achieve orbital motion. Like theoretically possible on the moon, right? Because it has no atmosphere. If you tried to do it on Earth, that wouldn't be possible because you'd have to throw it so fast that it would have a lot of air resistance and friction and so on, right? And so the tennis ball just couldn't maintain it. Plus, if it did try to maintain it, it would probably catch on fire from all the air resistance, right? And friction. But on the moon, this might be possible. Let's calculate what speed would be needed. So the idea is we've got the big R for our equation would be this, right? Let me just highlight with the big purple here. So this from there all the way to there is R for our equation, right? We can start analyzing this as FG equals FC, right? Or we could have just used the equation. But either way, we get there almost the same speed. You know what I mean? Like that's what I'm pointing out, is that the concept of force of gravity equals the centripetal, and the two equations meshed together to give this, I think is probably the better way to go about this. But if you're doing a bunch of these in a row, you're certainly just going to grab the V equals root of GM over R. Right? But this becomes, because of what we've done here, I'm hoping you're recognizing that if I had started the lesson with this saying, okay, so what speed? This would seem like it would be a pretty complicated thing to figure out. Like, oh my gosh, how can we possibly figure that out, right? It turns out it's pretty easy. We've already done all the hard work. We've done the hard work of understanding force of gravity and the hard work of understanding mv squared over r. So it just becomes g times m over r, root it, and it says, oh, you'd have to throw it at 1,678 meters per second. So multiply that by 3.6, 1678 times 3.6, you'd have to be able to launch it at 6,040.8 kilometers per hour. So I don't think that's something you're going to try and do with your arm, but times 3.6 gives us 6,040.8 kilometers per hour. So that's still really fast. But if you did launch it at that speed, it actually would be an orbital motion. Okay, it would stay at that 1 meter height, and you'd have to make sure to duck out of the way when it comes back around the other side and comes at you from behind here. Notice that if you're typing in 1.74 times 10 to the 6 plus 1, that's the same thing I always say about, like, that's like giving Bill Gates a penny. Is he now a bazillionaire and also a penny richer? Technically, but mathematically, he's still just the same billionaire, right? So you'll find that becomes irrelevant in there at that number, but that's okay. It just basically, I wouldn't bother typing or adding the 1, but if it feels good, you can add it. Anyways, so if you brought, yeah, like I said, a launching machine of some sort, you know, like a rocket or whatever, you could launch it sideways and have fun with orbital motion. Just try not to get hit by it. So that is not so bad. The other challenge question, and I want you to submit it, so it's becomes an assignment. So this is, I guess, assignment 6 in reality. Back to this, yeah. So 5 was the, wait, no. So 5, 6. This is going to be called 7. Yeah, let's call it 6, I guess. This one here, and again, this seems like a harder question than it really is. At first glance, you may be like, how the heck would you do this, right? But so I just need to describe what geosynchronous orbit is, and then you're going to calculate the distance would be for that. So if we're looking at Earth from above, okay, this is the North Pole. So we're viewing Earth from above, from our point of view, thinking that we're the top of the world rather than poor Australians being at the bottom. So we're looking down at Earth at the North Pole, and of course it rotates around, complete rotation in a 1 day, right? A satellite that's in geosynchronous orbit will orbit around right with it. So it'll always look, if you look up and see a geosynchronous satellite, right? So if you look up and see a geosynchronous satellite, it'll always be right above you, okay? Because as you rotate around during a day, it rotates around during a day also. Okay, what I'm asking is, I'm asking what height, determine the distance needed. Yeah, like distance needed for geosynchronous orbit. In other words, like we're asking, like what height does it need to be at? Okay, what height's needed for geosynchronous orbit? So if you're giving your answer as a height, I suppose we're looking for this number, right? Okay. So do you have a feel for how that would work? How that would calculate? All right. So that's the stuff for the new stuff from today, I should say. I might, and the solutions are all going to be posted for that to help you through it. So I'm looking at the course and trying to make sure we're going to be able to get through things. And the lessons that I put together, I'd labeled them as, what is there, 42A, 42B, 43A, and 43B, because really the only new one is gravitational potential energy in general. That's the only new one. 42A and B and 43A are absolutely pure review from grade 11. How do you want, I feel like I should include these lessons to help you. But I'm just wondering what you feel about it. So for example, what I'm wondering is, since we have an extra half hour of like on the clock time, I think you should put me to work in reviewing this with you. And I'm phrasing it that way on purpose because I want you to understand that lots of teachers would be like, cool, we're done for the day, I can go relax. But I think that you would be better served by seeing some review of concepts from grade 11 to help you tackle the new stuff in grade 12. But it can't be a 4-day affair because we have a grade 12 course we need to do. So the options are, I don't show you in this review and I just hope you know it, you hope you know it, or you work me really hard for a bit here and I show you some stuff. Does that make sense? What's the plan here? Do you want me to show you some stuff?
I think I prefer to see review.
Sure, mine as well.
It just makes sense. And so I'm trying to make sure, I'm trying to put the positive spin on this where I'm not working you like crazy. I'm actually working myself like crazy, right? Trying to help you. So that I want you to look at this in a positive light. So once this time ends at 12:00 whatever, right? You still have technically a half-hour class time still, certainly for starting the homework and so on. And then of course at grade 12 level, it's pretty standard to have half an hour to an hour from each class. That's the hard part about this quadmester stuff. Every grade 12 teacher from a science course in Ontario would agree that normally there'd be like say 40 minutes of homework each night. So 2 courses a day. Now we're talking about like hour and a half of homework each night ish. Oof, that's the quadmester system. If anybody says it's great, they're not a science teacher. Anyways, but the amount that we have from these isn't that much anyways. So I think we're okay. So I will show you some review. Okay, this brings us into the next unit, sort of, but it's all part of that motion unit, right? But we're starting to talk about the energy concepts, and also we're going to end up talking about momentum finally, so we can use the word legitimately rather than the way everybody uses it illegitimately and wrong in a lot of cases, like hockey teams with momentum because they won games or something. But let me just, I'll fly through this and as a review, you'll have a record of it, and hopefully most of this makes a lot of sense to you. Okay, so ready to go here. So energy momentum. Of course, we know that work equals the change in energy, right? Work done equals change in energy. So we're talking about a transfer of energy a lot of times rather than just like work done or change in energy, right? So this energy value, of course, can be positive or negative, but just like in the electricity unit, we know that it doesn't add like a vector, like up and down wise, but if you have positive energy, negative energy, they certainly do cancel each other out, right? They go against each other, but it's not truly a vector. You're never going to have a component or anything. But we know from grade 11, work equals force times distance, right? And so in grade 11, we thought of these just as scalars, where we're just like, oh, it's just FD cos theta, right? So the logic of this was, well, I'm going to show you this part, and I'll show the 2 versions here. So it's really not any different, but they call it F dot D, and I showed this in grade 11 as well. It's called the dot product, and the reason they call it the dot product is because they want to acknowledge that only the force in the direction counts, right, of motion. Only the force applied in the direction of motion counts. And so in math, they think of the dot product as a method or one of the ways in which you can multiply vectors. In physics, we think of it as logic, where only the force in the direction you're pushing counts for work done because it's the one that's in the direction you're actually pushing, right? And so we are already familiar with this, saying, oh, work equals force times distance, but it's only the component, right? If in the direction you're going, only the component of the force. And so that's really, again, reviewing, showing you, but it's really the same thing. So if I look at the F cos theta part, that's this, right? Which is really Fx to match the x direction of the displacement. So nothing new, really nothing new. It's just, if you saw it as written as a dot product, you'd be like, ooh, that's the grade 12 version for the rigorous mathematician part of the course, but meh, same stuff. So moving on here. So just as a review of this, if we said, okay, if we've got a 1 Newton force acting at 15 Newtons to the horizontal, and it goes this far, calculate work done. This is totally a grade 11 question. You'd be like, oh, force times, the component in the direction times the distance. If we saw the grade 11 version, we'd be like, oh, 10 cos 15. Oh yeah, so the 10 cos 15 times the 2 meters gives you 19.3 joules. Or in grade 12, maybe you don't talk about the component idea as much, but absolutely I prefer you do. Like, this is still fx, right? Like, goodness sakes, it's fx and it's delta dx, and it just, why would we pretend that doesn't exist? Why do some people, I should say. Units of this. Oh, my screen. Give me my screen back. All right, here we go. So newtons times meters, we know we're talking about work done. We've seen this unit analysis before too, right? Where kilograms meters per second squared, meters squared per second squared, sorry, is a joule of energy. So work times distance, obviously normal stuff. Keeping going, we're still good. You're reviewing and saying, yeah, I've seen this before. Yeah. All right. Throw the brakes on if you need, but the idea of positive and negative energy in a system, right? If we're looking at the total energy in a system, we can add up all the different kinds of energies, and you might have a positive, like you've added energy to the system, or you might have a negative, saying like the energy left the system, went to a different part of the system or transferred to a different part, right? So what energy did the object, what energy did the object or the system as a whole have in the previous example? Well, since there was no friction, then we know it accelerates, and so it gains velocity. There's another review lesson about the kinetic energy equation of 1/2 mv squared. But again, it's completely grade 11 review. But really what we'd be saying here for now is the total energy is, of course, we can tell like we added kinetic energy to the system, right? So that would be in there like a positive EK. If we had friction, if there was friction, if the velocity, if it had actually, specifically we're saying if that constant velocity due to friction, we're not actually getting kinetic energy. Instead, we just be converting to thermal energy. So we'd have like a ET or whatever you want to call it, right? A thermal energy in the equation. Or it could have been friction so that it's a little slower. So, or let's say acceleration with friction, FF, in which case there'd be some ET, some thermal energy, and some EK, right? So if this value as a whole was, say, what did we have before? Was it, we don't have to use the same numbers, but I think we had it there was, let's just round that to 20 joules to one significant digit. If this was 20, right, it could have been like, oh, let's have, 5 of it as thermal energy and 15 of it as kinetic, right? That's the energy in the system. If we looked at a question where there's a force that's slowing something down, then you think of the slowing down idea as we're taking energy away from the system. We're talking about negative work being done, so there'd be a negative in there. Okay. So energy of a system can change, but overall, of course, we're going to see multiple times that energy in a system is overall is conserved. And so you'd have one form of energy transferring to another within a system, but overall, the energy of the entire system, the universe, is conserved, or the whole system you're looking at. So that's this page here where we're saying the law of conservation of energy, of course, is you can't create or destroy energy. It can change forms. Let's leave that for now. It can change forms. Can it be quote unquote lost? Like, can it go to other forms and you can't find it anymore? Yeah, but it's not created or destroyed. The energy still exists. Okay, so it definitely can seem like energy was lost because it can go to other forms and you can't get it back very easily. So it's lost, right? Happens all the time with friction. Goes to heat, dissipates into the universe, hard to get it back, right? So we know the idea that we can change energy from one form to another, which is what's going to be called the work energy theorem. Work energy theorem. That's a fancy name for saying energy can change from one form to another. Okay. We looked at force displacement graphs. Really not necessary to spend time on this, but yeah, this is still force times distance, and so calculating work done. I'm only really mentioning this right now so I can briefly mention the idea of a calculus link. Well, clearly we're not going to do, but later on when you see calculus, I think it'll help you understand calculus a bit more. If we wanted to add up in a situation where we have non-uniform forces, like it seemed great in grade 10 and grade 11, right? Where we're like, ooh, I can get the area underneath and that's the work done. But what if the force wasn't, uniformly changing, right? In which case we'd have, non-uniform acceleration, we'd have non-uniform forces, or non-uniform change in the forces, I should say. If we're trying to estimate the area, it might look something like that, right? However you want to position this, would basically divide that thing into a bunch of rectangles, add up those areas to get an estimate, right? So that's what they did in calculus. They decided, you know what, if we make those rectangles be smaller and smaller, you can see that we're going to get a better and better estimate. The difference between the actual areas of the rectangles and the area under this portion of the graph is very small, right? Those tiny little corners. Whereas in this case, we had differences that were quite big. Luckily, of course, they kind of balance out, right? A little extra and a little not enough, a little extra and not enough, but they don't balance out as well as they do when you have small rectangles. And so that's what calculus is you add up the areas into the curve, for smaller and smaller time intervals, and you actually estimate, but really calculate the actual value. Rather than getting an estimate, you think of it as, hey, we're able to clue in, or we're able to calculate the actual value. Okay. So yeah, calculus turns us into really precise numbers where you're like, you don't need to, this is just for interest, you don't need to worry about this, but it's going to help you when you see calculus later on, right? You're talking about the limit of the addition of all of these rectangles. This means addition of the rectangles, and you're looking at the limit of this as the the size of the rectangle you're using gets smaller and smaller. And you've seen this once with me already in this course. Okay, so the addition of all those areas where you're talking about smaller and smaller areas, this limit of the sum is awkward and lots of writing. So they eventually decided, hey, let's simplify this. Let's just call it, let's just have this symbol. And they called that an integral symbol. So this is an integral. And all it means, though, when you're doing integrals later on in calculus, right? Integrals are just a limit of a sum, right? A bunch of things added up, where the things you're adding up are smaller and smaller in order to be able to get a better and better estimate. So that is not even part of this course. It's just basically to help you in the long run when you see calculus later on. You'll be like, oh, okay, I remember that stuff. That was to try and get approximations. Okay, so that's review number 1. Now, along with the review number 1, this is not meant to be a stress assignment. These are questions that are to do with that review. So if you can take a peek at some of them and make sure to be like, yeah, obviously this is stuff I can do, it's stuff that I've seen, then you're on track. If not, you've got a little bit of work to do to get it so that you can do those. Okay. All right. Let's do it again. Work energy theorem. This is the one that shows kinetic energy, which is, again, review from grade 11. I looked at the calendar, number of days left, number of lessons left for the grade 12 curriculum, and we're super close. So if we do a little bit like this once in a while, like when it makes sense to do so, it'll actually free us up to be able to do a little less on new curriculum once in a while as well, and also make sure we can finish the course. So I think we're on track to finishing the course in a reasonable manner, as reasonable as it can be in a quadmester system. So this is work to kinetic energy. The work energy theorem, we know it's the idea of transferring energy from one form to another. Physicists tend to think of kinetic energy as the only real kind of energy, and everything else is potential energy. I don't know why. I still think of kinetic energy as a potential energy as well, because if a baseball is coming towards your head with lots of velocity, it has more potential to do damage, right? So to me, kinetic energy is still a potential energy, but So in general, basically work energy theorem is network. Energy can change its total energy, like work equals, it's just a fancy way of saying work equals delta E, right? Work done equals transfer of energy. So I didn't even really need to show that page, I suppose. So specifically here, going to kinetic energy, we know that work done transfers energy, and we know that work done is like a force times a displacement business, right? And so we know it's delta E. And so we're going to look at how a force causes acceleration, and so it's going to make it speed up, and so it's going to gain kinetic energy, and so basically we're going to say, okay, the work done is the change in the kinetic energy, right? This is just a review from that other page about how if we're talking about an angle, of course, you're going to have the angle in the question, right? Same as the grade 11 version. So a lot of stuff shown here, but it was just to sort of set the stage for what we're doing. So we got work being done, and we want to just confirm this 1/2 mv squared equation is what this page is about. So we have work equals force times distance. Force equals mass times acceleration. So we're substituting that concept into this, this work equals force times distance concept. The mass times acceleration concept got subbed into that. The angle, if we have the angle 0, we could simplify our life and have a cosine of, cosine of 0, so it becomes a 1, right? If the force is in the direction, all of the energy becomes the kinetic, and we get the full equation. So work equals delta E K, as we talked about. Acceleration equals delta V over delta T. So that's another concept substituted in. And then the weirder one to substitute in is what the displacement would be. But we're talking about a situation where we're accelerating. And so we can either use the displacement from the graph, which is 1/2 times the delta T, like the base times the height, or, and also because the velocity is in comparison to 0, we can just say V instead of delta V if we want. That's the same as before when we're talking about the potential, electric potential. Technically, it's a difference from infinity, right? At 0 and infinity. So if your velocity is, if you have a delta V of change of 10 from 0, obviously you have a velocity of 10. So that's why delta V can just be written as V. Yeah, so we have those things substituted in. Oh, I was going to mention here too, this could have been the equation. Would have been like V1 delta T plus 1/2 acceleration delta T squared. We could have used that equation instead of the area one, and it would instead of the area and the acceleration combined, I should say. But it's easier with the way we're showing here. So basically, I hope you've followed here that I've substituted MA in, and I've substituted delta V over delta T, and I've substituted in a 1/2 delta T delta V, justified that it can be just velocities, and so those simplify to be 1/2 mv squared. Because we know F equals MA, and we know acceleration equals delta V over delta T, and it's just 3 different concepts being combined basically to give you an equation. Right, so the kinetic energy equation, we've seen this development before, just more fresh in your mind now, and the equation's more fresh in your mind. So obviously, this is a little tip. You might have, I think I've showed this well in grade 11 too, but just in case you've forgotten about it, you can't look at this and say, ooh, that's a change of 3 and 5, so a change of 8. You can't say it's a change of 8 and expect to get the right numbers. And it's because algebraically, A take away B squared is not the same thing as A squared take away B squared. The numbers just don't work, okay? Numerically, that's not true. And so the physics concept attached to those numbers isn't true either. The correct way is to look at the change being the final minus the initial. And so you have to do the A squared take away the B squared in their own right? Like this A take away B squared is not the same. You have to do the final minus the initial. Okay, so we have to do the 1/2 mv squared for the final minus the 1/2 mv squared for the initial, and you get your correct change in energy of 176 joules. Okay, we could even justify this further if I had like a certain force, right? So if there was a force that was given, then we'd be able to calculate the amount of acceleration that was there, and we'd be able to say, okay, so the work done was, so basically we'd be able to get work done equals, 176 based on the work equation, and then see, oh, okay, so for talking about kinetic energy, this is the correct analysis. Certainly something we could do in a complete analysis. Okay, but just make sure you're not doing a delta V squared ever. Okay, because that's just not true. Confirmation of the, oh, this is what I was talking about, we could show things, right? So if we had an acceleration of 2, and that meant we had a force of 4 newtons, then what do we have here? Work done would be force times displacement, which would be the 4 times the 44. The 44 comes from analyzing what kind of displacement we get with those forces and those accelerations, right? So you'd actually calculate out, we end up with 44 meters of displacement. And so the amount of work done is, it matches, like I said. I just put it in reverse order, I guess. So does that seem familiar? The idea of kinetic energy, 1/2 mv squared? Please say yes. Someone. It must be, right?
It does seem familiar.
Yeah, like that's it literally just grade 11 stuff. It's just, if you don't have this under control, it's going to make the next thing we do kind of tricky. So 43A, and I'll leave the new one, of course, for tomorrow, to start tomorrow. But the gravitational potential energy one is also, it's the in general one that's new. Here we go, just making sure I'm loading the right one. So the last one, three review little help things for you. And then I'll save the new stuff, of course, for end of the lesson. So this is just Fg equals mg delta h. We've seen that in grade 11 as well. Of course, Eg equals mg delta h, not Fg. Right, the work done by forces against gravity. So a minute here. All right, so like I said, gravitational potential energy equals mg delta h, or mgh if it's changed from 0. So this is like near the Earth's surface. So obviously the next thing is going to be to talk about, oh, well, what if we did work to move an object hundreds of kilometers into the air? Clearly this formula is not going to cut it, because our new information we saw today was that the g value of 9.8 is not going to stay the same. And so tomorrow we're going to calculate how to look at changes in energy on large distances. That's why we need to be able to do it. But the mg delta h stuff, first of all, was of course just work done, and we're just lifting against the gravity force. And so it was pretty easy development back in grade 11, where it was like force times distance. The distance is delta h, so it's mg delta h, right? Because the force is mg. So it's like a super easy development, okay? And then of course we did calculations to do with that, where we're like, oh, well, if you carry an object up a set of stairs, you need to figure out what height you actually lifted it, and just do your mg delta h, right? So in this one here, the height, the 4 meter long staircase at an angle of 32 degrees, you can use what, tan, right? Or no, sine, opposite over hypotenuse, right? So sine of 32 is going to be opposite over hypotenuse. Get your delta h is 2.1, right? So then mg delta h would just be the mass times the gravity times that 2.1. So what I analyzed right here led for us to be able to say, oh, perfect, mg delta h, we got it. All right. Now, obviously, it matches the idea of lifting with a constant force of gravity to get a constant velocity up, and you've got your lift force, you've got your distance you've lifted, but at this point, I'm thinking, why would we do all that? We just developed that equation. So I'm thinking more along the lines of mg delta h, of course. Okay, but this is true. It's just basically pretending we didn't actually get an equation that we should use instead to make life easier. Okay. This is just the conservation of energy equation page again. And so I just should show you this one to make sure. We've done this lots of times in this course already, but don't miss out on this idea here, right? Where you're like, okay, total energy equals all the energies added up. Certainly we can have one form of energy transferring to another. So if the gravity number gets smaller and this one gets bigger, both by 10, let's say minus 10 and plus 10, you can see the total energy would stay the same, right? It also allows us to be able to solve and say like, oh yeah, so that gravity energy became the kinetic energy, like I've shown you before in this course already. So it's actually a bit of a review from this course, really. So if we had a 4 kilogram object and an 8 kilogram object, both falling 2 meters with no air resistance, we want to determine the final velocities. And of course, we should be able to recognize right away, looking at this, that mass doesn't matter, right? In this equation, it makes it even nicer to be able to see that mass doesn't matter, because we have our mg delta h concept that we just looked over from grade 11, and our other one that we just looked over from grade 11, 1/2 mv squared. Okay, masses don't matter for velocity. Velocity. Right? They do matter for how much force is involved, but they don't matter for velocity. So we're able to just cancel out the masses and determine the speed. Right? Therefore, it would end up with 6.26 meters per second. If you wanted to confirm any of this, you'd be like, okay, well, we got an acceleration of 9.8, we've got a distance, we've got initial velocity of v1 is 0. You could calculate out that final velocity just as a uniform acceleration equation. I don't think this does it though, does it? That's just basically the same analysis, but let me just make a note here. Note, you can confirm this, right? By calculating final velocity based on the uniform motion. Right, using your regular equations, you got v1 equals 0. We've got acceleration equals 9.8. I'll just put numbers in roughly here, right? Not worry about minuses and so on. And we've got delta d. So I'll say displacement equals, I don't want to find the delta button, but 2 meters. All right. And so obviously you can figure out that final velocity as well. But so it is neat to see that you can calculate, you know, there's these different realms, these different branches of a physics curriculum where it's like, you know, they better agree with each other. And so as a review for yourself to see if that makes sense, you know, wouldn't be a bad idea to calculate the, you know, what the velocity should be based on uniform acceleration analysis, because it helps confirm that the energy stuff that we just reviewed over really does work and make sense. So each one of these, I have picked out the equation or the questions that are to do with this stuff, but you know, the kind of practice that goes into these is what you've already done in grade 11. At this point, reviewing it to make sure you're still able to do that. And that gives us a good jump on being able to tackle the next grade 12 concept. Okay, so I appreciate your patience and attention and so on, and I hope that helped you. It's clearly a review of what we've done, and you have practice questions to look at as well. And if you need any help with those, by all means, let me know. I can send you solutions and that. But yeah, it is review. Alrighty. So
Mr. Horn,
yeah, go ahead.
what day is the second assignment due, like the orbital one?
So that's the gravitational, yeah, the synchronous one. So let's go in. I'll say for sure here what we decide, but how much time do you feel you need? Like if I were to say tomorrow you're gonna hate me and stress out and so on, so I'm certainly not doing that. I'm wondering if maybe Friday would be good.
Okay.
That would work, right? So geosynchronous, let's make that guy do Friday. Edit assignment. Do Friday. I'm talking slow motion here. All right. 28. And it always comes up as just before midnight, which is perfect because that's what I always have been saying. Friday at midnight. The only illogic with that one is help. Well, that's fine. Good enough. Maybe I should make it. Nah, that's fine. Friday. I already said it. Some speed. That one's done. That one's done. And then the Gravitation is obviously due tonight. I might as well put a due date on that one while we're here too. But any questions? I didn't assign this one yet. I'll hold off on that. There's a uniform acceleration question. I'll email it out. It's a catch-up question. It's the new stuff we've done from grade 12. We just didn't do an assignment to do with it. So I want you to do one, but I don't want to overload you with too many all at once. So maybe I'll hold off on that for a little bit. But okay. So focus on getting the other ones done. Wait, when this one gets sent out, you only have one to work on. All right. So stopping the recording.